My name is Yvonne Chart, and I am a second-year PhD researcher at the University of Oxford with the Posture Group. And today I'm going to talk to you about some of my research using the plasma-focused ion beam microscope to investigate lithium metal in batteries. So first I want to talk about what is a focused ion beam microscope. So you might be familiar with a scanning electron microscope, or SEM, and a focused ion beam is similar to that, but instead of using electrons to image a material, you're using ions. Often those are gallium, and in this case we're using xenon. So there are a few differences because we are using more massive particles to image. First of all, they're more surface sensitive because as the particles are more massive, they can't penetrate as deep into the sample material. Second of all, again, because they are more massive, they can mill into the material, actually cutting in and revealing some of the internal structure. And finally, we can use a gas injection system to also deposit material on the surface. And by depositing ions and different gases, you can actually link up different aspects of your sample using, say, platinum or copper. Often, a focused ion beam is used in tandem with an SEM so that you can mill with your ions and image with your electrons at the same time and get the benefit from both of these techniques. So how are focused ion beams often used? So as I was saying, you can use them to mill or deposit material. And often you can see this on absolutely tiny length scales, nanometers. So this can be used for nanomachining and in nanoelectronics, things like that, to connect up very, very small electronics. Enables some very, very interesting research there. It can also be used to prepare samples for transmission electron microscopy, or TEM. And in TEM, the samples have to be transparent to electrons. So that means, again, they have to be extremely thin, and you can use an ion beam to thin your sample down until it reaches that transparent level. Finally, we can use it to cut through a sample and reveal internal interfaces and the internal structure of a material and to learn more information about what's going on inside of a sample that you wouldn't normally be able to observe. So how am I using this technique in my research? So my research focuses on batteries, and so I am looking at battery interfaces and using the focused ion beam to look at what's going on inside of a battery. So there's three key parts of a battery. We have a cathode, an electrolyte, and an anode. So our cathode and our anode are both electrically conductive because we want electrons to be able to pass through them and go out in an internal circuit, power your phone or your computer, and come back around the other side. Meanwhile, your electrolyte should be an insulator to electrons, but conduct ions. So ions can go across, and this is what happens when you charge and discharge your battery. As you do that, the structures inside your electrodes, anode and cathode, and your electrolyte can change. But in general, we want there to be good contact so that we can obtain that good conductivity, whether it's for ions or electrons, across the battery. So we can investigate that using a focused ion beam to cut through and see how the internal structure of a specific part or the interface between two parts it appears before, during, after we use a battery. So first I'm going to focus on solid electrolyte and the cathode because they are a little bit easier to investigate, and then I'll go on to why the anode is a little more difficult to investigate in a second. So first of all, we have the cathode, and pardon me. We can see here that we have different types of particles in our cathode, which all have good contact with each other, and there are only minor voids that you can see in this image, and the contact between the cathode and the electrolyte here is fairly good. So this material is actually fairly well developed and performs quite well. On the other hand, we have a solid electrolyte, which is a little bit earlier in production, and there are some larger voids and a little bit more disparity in particle sizes. And so this is something that is still in development. We can investigate how different techniques to manufacture new electrolytes either improve or do not improve the structure of this electrolyte. So now we're moving on to the anode. And this is a little bit of a problem because if we try and look at anode materials, which is a lithium metal, this is the type of anode that I'm interested in, it looks like this at room temperature. And this is actually just due to beam damage. It's not the true internal structure of the lithium anode. So we needed to find a way to actually preserve that structure and prevent the lithium from looking like this. The main reason why this occurs is because lithium has such a low melting temperature. So as you shoot ions at it, it warms up, and you lose that structure that you would normally see. So by imaging it at cryogenic temperatures using liquid nitrogen, we are able to preserve that temperature. And we actually installed a cryogenic stage fairly recently, and so we're now able to get nice, smooth images of lithium like this, and we'll be able to hopefully investigate some more complicated structures soon. So what I'm hoping to do with this is to investigate the performance structure link between of the lithium metal anode. So we can see, we're measuring the performance here using the Coulombic efficiency, and this is the amount of lithium that is recovered after each cycle, so after every time you charge and discharge your battery. And this is, in this study, they compared 3 different electrolytes. And so the first one had the lowest Coulombic efficiency, so that's the worst performance. And you can see lots of big holes and gaps in this structure, and not a particularly good interface either. Meanwhile, for the other 2 electrolytes, we both of which see a much better performance. There's a much more connected structure, and the interface is much stronger. So they were able here to correlate this structure with better performance. So with that, I would like to thank my group, the PASTA group, for their support of this research, LISTAR, which is part of the Faraday Institution, for funding my PhD, and Royce for funding the equipment. Thank you very much.